Welcome everybody to our second colloquium talk this spring, and I'm glad that everything takes place on site still. Let me start with a short technical thing, like we cannot hear people on Zoom, so please, if you have any questions during the talk or at any moment, write in the chat. I will observe the chat anyway, okay? And then right away more to the mathematical side of things, so like today's speaker will be John Keating from the University of Oxford. It's my pleasure to introduce him first before he will speak. So John Keating did his PhD in 1989 in the University of Bristol, where he managed to stay actually and became professor in 1997 after the usual career steps. And he stayed there for the longest time until very recently he moved to Oxford like 2-3 years ago, in 2019, where he's professor since then. His research goes about quantum chaos, random matrix theory, and connections to number theory. And he's currently holding an ERC advanced grant supporting this type of research. In the past, his research has been recognized, for example, by a fellowship of the Royal Society, and most notably, maybe in the context of today's talk, also the Fröhlich Prize of the London Mathematical Society, I think. Right. And this prize is usually handed out for or awarded for original and extremely innovative work in any branch of mathematics. That's how the prize is defined. And it was awarded in recognition of his seminal work on the modeling of zeta functions via random matrix theory. And that links exactly to John Keating's talk today, and it's a great pleasure to have him as a speaker here, talking about random matrices and Riemann zeta function.
Good, okay, well, thank you very much for the very kind introduction. Very good to be here in front of a live mathematical audience for the first time in several years. My first trip outside the UK for 3 years. Feels very good to be talking mathematics with people again. So indeed, what I'm going to speak about today is a connection between random matrices and the Riemann zeta function. And this connection has its birthday this month. It was first proposed 50 years ago this month, and I shall show you the precise date where it was put forward. And it's a highly surprising connection. It's not at all obvious that these two subjects would be related in any way, but it's been profoundly important over the past 50 years, and I'll try to give you an indication as to why that is. So I'm going to start by telling you a little bit about the Riemann zeta function, and then I'll go on to tell you about random matrices, and then tell you what the connection is between the two and how we see this as part of a broader picture, and how it's been influential in both sides, both ends of the bridge, so to speak. This, I think, isn't working. Anyway,
Sorry, it's now it should work.
Perfect, thank you. So, so the theory of the zeta function has its origins in attempts to understand the distribution of the prime numbers. So here are the primes up to 100. And of course, this list continues, and we've known since the time of the ancient Greeks, since Euclid, the list continues forever. But beyond that, one can ask more fine-scaled information about the distribution of the primes. So it was observed a long time ago that there are quite a number of primes. There are 4 primes up to 10, and then 4 in the teens, 2 in the 20s, 2 in the 30s. So to some extent, you might say the primes are getting a little less dense as you go up. And this has been observed frequently. And this was quantified in a famous achievement of 19th century mathematics, which is the prime number theorem. So if pi of x denotes the number of primes less than or equal to x, then the asymptotics of pi of x is just the logarithmic integral. Integral of 1 over log y dy from 2 to x. And so roughly speaking, the number of primes up to an integer x, below an integer x, is asymptotic to x over log x, so the primes get less dense as you go higher up, logarithmically. And this is quantified by the prime number theorem, as I say. So the origins of this go back 100 years before the proof of the prime number theorem, and the precise quantification was conjectured first by Gauss. So this is an extract from a letter from Gauss to his former student Encke in 1849, where Gauss reminisces about the origins of his suggestion that the prime should have a logarithmically decreasing density. He says, your remarks concerning the frequency of primes are of interest to me in more ways than one. You have reminded me of my own endeavors in this field, which began in the very distant past, 1792 or 1793. So for those who know when Gauss's birthday was, that puts Gauss at about 15 or 16 years old. One of my first projects was to turn my attention to the decreasing frequency of primes, to which end I counted the primes in several chiliads. A chiliad is an old-fashioned terminology for 1,000 consecutive integers. So Gauss was looking at ranges of integers with 1,000 integers in them and counting how many primes lay in those intervals. I counted several chiliads and recorded the results on the attached white pages. I soon recognized that behind all of its fluctuations, this frequency is on average inversely proportional to the logarithm. So Gauss had suggested or proposed this logarithmically decreasing density, but it took about 100 years to prove his conjecture. This, out of interest, is the data that Gauss recorded in his own handwriting. So this is Gauss saying that up to 500,000, there are 41,556 primes. And if you compute the logarithmic integral, you get a number very close to that. You get 41,606.4. So Gauss had to do two things. First of all, he had to count primes up to 500,000. Then he had to estimate the logarithmic integral. Neither of those are trivial steps. And the difference is about 50. Ignore the last column. That's a peculiarity. I won't speak about that today, although I could do it. It's quite interesting. But I want to focus on the first three columns. Up to 1 million, Gauss counted 78,501 primes. He was out by 3. So in fact, that's an overcount by 3 of the actual number of primes up to 1 million. But that's a small number. 3 is a small number in this context. The logarithmic integral computes to this, and again, the difference between the actual number and the logarithmic integral is very small. And Gauss went up to 3 million. He counted 216,745 primes. If you think he was 15 or 16 years old, this is what you can achieve when there's no social media. This was his data, and this is what led him to speculate on the logarithmic integral as the correct formula, and 100 years later it's proved. Now, of course, we know that this difference is small, and one of the great problems in mathematics is to understand exactly what the size of this difference is, and that's an unsolved problem to this day, to understand how big the difference is. I'll say more about that later. So how was this proved? Well, the key step was made by Riemann in 1859, who suggested that one way to prove the prime number theorem would be to use analytic properties of the Riemann Zeta-Function, zeta of s, which is defined, actually was constructed by Euler earlier, but was understood by Riemann as a function of a complex variable. It's defined either by a sum over the integers, the positive integers, or a product over the prime numbers. And these are equivalent to each other, and that's an elementary statement that follows immediately from unique prime factorization. And these formulae converge if the real part of S is greater than 1. You see why the zeta function is connected to the primes. That's because of this formula here, which is due to Euler, that says that if you can compute the zeta function, you're getting information about the prime numbers out because the zeta function is constructed from the prime. So if you can deconstruct the way this product produces the zeta function, you can infer information about the distribution of the prime numbers. In particular, the logarithm of the zeta function is a sum over the primes, and so it will have interesting structure where the zeta function is singular, or where if it has a singularity or a zero. The logarithm of the zeta function has its singularities where the zeta function is either singular or zero, and that information will transfer to the distribution of the prime numbers. So the zeta function has a continuation to the rest of the complex plane, apart from a pole at s equals 1. It satisfies a functional equation, which is a symmetry of the function. It says that if you get the zeta function and multiply it by a gamma function and a power of pi, the resulting function is symmetric under s goes to 1 minus s. So it's a reflection symmetry through the line, real part of s is 1/2. And this was proved by Riemann. It was guessed by Euler on the real line, but yeah, that's true. But proved as a function of a complex variable by Riemann. And the trivials, it follows straightforwardly from the functional equation that the zeta function has trivial zeros, that is, zeros that we know exactly where they lie and what their properties are, at the negative even integers. But it also has non-trivial zeros, zeros that are much more mysterious, and these have a real part between 0 and 1. So they lie in a strip bordered by the lines real part of s is 0 and real part of s is 1, and they have non-zero imaginary part. And these are the non-trivial zeros contain all the information, all the non-trivial information about the distribution of the prime numbers. We know everything else about the zeta function. It has a pole, it has trivial zeros, it's a meromorphic function other than this pole, and so all the subtlety in the distribution about the prime numbers comes from the non-trivial zeros, which contribute singularities to the logarithm of the zeta function. So of course these non-trivial zeros are famous. They're the subject of the Riemann hypothesis, which says that they all lie exactly on the symmetry line of the functional equation. That they all lie on the line with real part of s is 1/2. So put another way, if we denote the non-trivial zeros by a 1/2 plus i tn, then all of these numbers tn are real. And that's the Riemann hypothesis, one of the great problems of mathematics, still unproved to this day, and a famous problem in our subject, of course. So this has been the source of a great deal of study. We now know that the Riemann hypothesis is true for at least 42% of the non-trivial zeros. So we know that there are infinitely many of them, we know that, and at least 42% of them do lie on this line, and it's believed that all of them do, but we're far from proving that. This is a picture of the zeta function, or rather it's the argument of the zeta function, represented by different colors. So the colors are the argument, and you see that where the argument isn't defined are at these points. This point is the pole of the zeta function. These are the trivial zeros at the negative even integers, and these points here are the non-trivial zeros. And the claim is that all of these non-trivial zeros lie on a straight line in the complex plane. The line real part of s is 1/2. And we know numerically, via exact numerical calculations, that the first 10 trillion zeros do lie on that line. That's 10 to the 13. And we know that batches much higher up than that do lie on the line. So every zero that's been computed, of course, lies on the line. And we know that it's true for ranges of now billions of zeros up near the height of the 10 to the 36th zero. That's the world record at the moment. How do we know that? Well, the functional equation can be used to make the zeta function on this line, the line where the non-trivial zeros lie, the functional equation could be used to construct a real function on that line. And this is a plot of that real function. It's usually called the Hardy Z function after G.H. Hardy. And so as a real function, it's easy to plot. It's easy to see where its zeros lie. And here are the first zero, the second zero, third zero, etc. And the Riemann hypothesis is equivalent to saying that this function, other than down here, below 10, has no no positive minima and no negative maxima. And so what you're seeing here is a manifestation of the Riemann hypothesis. This is the Hardy Zeta-Function plotted a little further up, just beyond 1,000, and you see it oscillates. It's a rather irregular function, and one can use this to find zeros of the Zeta-Function, and then one has to just check that there are no zeros off the line, no positive minima or negative maxima, which would correspond to zeros off the line. So why might the Riemann hypothesis be true? Well, there's a famous sort of anecdotal suggestion which goes back to Hilbert and Polya, although in fact it seems from the historical record that Hilbert's role was rather minimal in this, and in fact the original suggestion almost certainly went back to Landau. So the Hilbert-Polya conjecture, as it's now called, or idea, is that one might try and prove the Riemann hypothesis by showing that these numbers Tn, which are the heights of the Riemann zeros at the critical line, are the eigenvalues of a self-adjoint operator. So then they'd have to be real. And so this suggestion has been very important in 20th century and 21st century mathematics. There have been many attempts to construct self-adjoint operators or operators with other symmetries whose eigenvalues coincide with the zeros. That is, there have been many attempts to construct a spectral interpretation of the zeros, and if that could be achieved, that would be a route to proving the Riemann hypothesis. But so far that's not been successful. However, it has suggested that one might investigate, even if one can't find the operator whose eigenvalues coincide with the Riemann zeros, one might ask whether the Riemann zeros do behave like the eigenvalues of an operator in some way or other, in some generic way. And this leads us to think about random operators. So how does a typical operator behave? Let me make that question more precise, but the motivation is that if the Riemann zeros are the eigenvalues for an operator, if we look at typical operators and we infer properties of their spectrum, does one see those same phenomena in the zeros of the Riemann zeta function? So random matrices are an attempt to model what typical operators look like. The idea is you start with a space of matrices, for example, the space of n by n real symmetric matrices or n by n complex emission matrices, and you associate with that a probability measure so that each matrix has a probability associated with it, and then one can ask for typical properties within that space of the say the eigenvalues or the eigenvectors of the matrix. So one can ask very precise mathematical questions about matrices if one associates a measure with them, and one uses this as a model for typical operators. And one can answer these questions now exactly or asymptotically as the matrix size tends to infinity. So this has become a very important area of mathematics and mathematical physics. It has an interesting history, which I'll mention in passing, because I think it's one, for me, it's very, I'm very curious as the history of these things, because its history goes back, has many different roots. So the historical threads that led to random matrix theory were, first of all, questions that go back to the end of the 19th century to Hurwitz about what it means to make a random rotation. So a random rotation in the plane, well, rotations in the plane are parameterized by an angle, and so one's simply choosing an angle at random. And Hurwitz asked what would it mean to make a random rotation in a higher dimensional space. Well, one knows that rotations are generally generated by orthogonal matrices, so Hurwitz was prompted to ask, what does a random orthogonal matrix look like? What are its properties? And so he constructed a probability measure on the space of orthogonal matrices which we would now recognize as Haar measure on the orthogonal group in 1897. And he even asked the question about how this would generalize to other Lie groups. So he even was thinking about random unitary matrices and random symplectic matrices. This thread was picked up in the 1930s by Hermann Weyl, who wrote a famous book on what we would now call random matrices associated with the classical compact groups. And it was brought to a very precise form and investigated in considerable detail by Freeman Dyson in the 1960s. And since then, many people have contributed to this subject. It's an extremely important subject. A second completely independent thread started with John Wishart in the 1920s. Wishart was a data scientist, as we now call them, a statistician, working in an agricultural research centre in England. And he was contemplating how one might look at the data coming from different crops, yields of different crops in different years. And he wanted to combine all this data together, so you've got data for different crops, barley, wheat, I'm not sure I know what other crops are, but apples, let's say, and you've got them labeled by crop and by year, and so he combined that data into a matrix, and then wanted to know whether the data he was seeing were completely random or whether there were any patterns within it. So he had to ask what random matrices, how they would behave, and this started a field that's now incredibly important in statistics. So this was picked up by Fisher and many others in the 1930s, and since then it's become one of the central planks of modern statistics. Another, as far as I can tell, completely independent historical thread goes back to the Manhattan Project in the US in the 1940s, where there were some highly complex numerical computations that had to be performed using linear algebra, and people started to wonder what the stability was of computations involving large matrices. So, for example, if you've got a system of a large number of coupled linear equations, how stable is it to solve that system of equations? And this was asked by von Neumann, who realized that one might investigate this by looking at random systems of linear equations, that is, by inversions of random matrices. And he wrote a very influential paper in 1947, which started off another very active thread of research. Within the context of what I'll be talking about, the history, I would say, goes back to Wigner in the 1950s, almost certainly not independent of von Neumann, because Wigner and von Neumann were school friends and worked together in Princeton. So my speculation, and it purely is a speculation, is that Wigner picked up the idea from von Neumann. In quantum mechanics in the 1950s, there was a lot of interest in solving for larger and larger systems of quantum particles, for example, nuclei of heavy elements. The energy levels of quantum systems, eigenvalues of a matrix. That's Heisenberg's great insight. And Wigner realized that it was sensible to think about statistical properties of quantum energy levels and to investigate that by looking at statistical properties of eigenvalues of random matrices. So this was his great insight, and again, this was picked up by Freeman Dyson in the 1960s, and then used by many people to model complex quantum systems. So Oriol Boigas and colleagues, and Michael Berry in the 1980s. And this is now the standard way to model statistical properties of energy levels in complex quantum systems. A completely independent thread goes back to Robert May in the 1970s, and this was questions about stability of populations of animals or species of plants or animals. So the question in biology at the time was, if you've got a large number of species that interact with each other, do the interactions make the populations more or less stable? And May realized that this could be written down as a simple model in terms of an eigenvalue problem. So a linear problem that represented the populations of the different species. and that if you treated the interactions between species as random, it was natural to model this using random matrices. And so he wrote a very influential paper then, which is, again, has been gone on to spawn many further studies. It's now very popular in mathematical finance. This is largely an application of the ideas coming from statistics. It connects with many other areas of mathematics, often in highly surprising ways. And you've got a wonderful, tremendous group here in Stockholm, which has led the world in this area. Kurt Johansson and colleagues have done wonderful work on seeing connections between random matrices and various areas of combinatorics or enumerative geometry. And finally, it's now finding many applications in machine learning. But I won't talk more about that. The connection I want to talk about, which is perhaps the most surprising of all of them, relates the Riemann zeros, which I told you about earlier, to random matrices. So this connection, I'll tell you about its history in a little while, but let me tell you what the connection is. The suggestion was initiated by Hugh Montgomery, who was a PhD student at the time, and Freeman Dyson, who we've already heard about, was one of the creators of random matrix theory. And between them, they realized that there should be a connection between statistical properties of the heights of the Riemann zeros up the critical line, those points that we saw earlier where all the colors met. If you analyze the heights of those points statistically, they suggested that there should be a connection between the statistical distribution of the non-trivial zeros and the eigenvalues of random matrices. And there are many ways to phrase this, but one way that I shall pursue is the following one. Let's start with the zeros of the Riemann Zeta-Function, the non-trivial zeros, so denoted by half plus I Tn. And these numbers Tn are meant to be real, according to the Riemann hypothesis. And we're going to compare the sizes of the Tn's to the eigenvalues of a random matrix. And to that end, we'll consider an n by n unitary matrix. We'll look at its eigenvalues, which lie on the unit circle, and we're going to compare the statistical distribution of the Tn's to the statistical distribution of the theta n's, the phases of the eigenvalues of A treated as a random matrix. I'll assume the Riemann hypothesis, so that's not strictly necessary, but it just makes the explanations a little easier. And then we want to compare the two, so we need to know what the right units are to measure them both in. And the right units, according to Montgomery and Dyson, are that you get the Tn's and multiply them by their logarithms to get a set of numbers Wn. Basically what that does is the Tn's get logarithmically more dense as you go higher in the complex plane, and you're just undoing that logarithmic density to get a set of numbers Wn whose mean density is 1. So the mean separation between the Wn's is 1. Likewise, for the theta n's, there are capital N of them, and they lie between 0 and 2 pi. And so we want to undo that density to get a set of numbers with density 1. So we multiply the theta n's by n over 2 pi. N's the size of the matrix. And then Montgomery and Dyson suggested that we compare correlations between pairs of Wn to correlations between pairs of phi n in the following way. So we get pairs of Riemann zeros, labeled n and m. We take the difference between Wn and Wm. So these are the Riemann zeros scaled so they have mean density 1. And we form all differences between the first capital N zeros of the zeta function. We look at differences between the Wn's and the Wm's, and we form some function of that difference. Doesn't matter which function. We divide by capital N and ask if there's a limit as capital N tends to infinity. And their conjecture, Montgomery's conjecture, was that this limit does exist, and it's equal to another object which is constructed from the eigenvalues of our random matrix. So in the following sense, we start with our matrix A. We scale its eigenvalues to have density 1 on the unit circle where they lie. We form differences between pairs of eigenvalues, phi n minus phi m. They depend on the matrix A. We form the same function of the differences. we sum over all pairs of eigenvalues, divide by capital N, and now crucially, we average over all n by n unitary matrices. So this is where the randomness comes in. This is computed, it's an integral that you compute with respect to harm measure on the unitary group, measure that's invariant under unitary transformations. And then you take the limit as matrix size tends to infinity. And the remarkable conjecture is that these two objects should be the same. So that's highly surprising that correlations between the zeros of the zeta function should be the same as correlations between the eigenvalues of random matrices. And this is very important because on this side of the equality, we can compute things. So we actually have a precise formula for what this limit is. And this had been computed by Riemann Dyson 10 years earlier. So the right-hand side of that conjecture is actually a theorem that's equal to this integral. So for any function f, you compute the right-hand side by integrating f against this kernel, which is a very famous formula in random matrix theory, 1 minus sine squared pi x over pi squared x squared. So if the zeros of the Riemann zeta function were completely behaved like uncorrelated random variables, this term sine pi x over pi x all squared would be absent. So if the Riemann zeros were like a Poisson point process, this term wouldn't be there. And its appearance in the conjecture is indicative of highly characteristic correlations between the eigenvalues of random matrices on the right-hand side and the zeros of the zeta function on the left-hand side. So this all boils down to the statement that the Riemann zeros are correlated in highly subtle ways, and those subtle ways are the same as the correlations between the eigenvalues of random matrices, which you can compute. So this was the suggestion that Dyson and Montgomery came up with. I'll tell you a little bit about the history in a minute. But how might you go about proving this? Well, how did Montgomery and Dyson come up with the conjecture in the first place? Well, it was really a calculation of Montgomery. He knew nothing about random matrix theory. I don't think he'd even heard the term. He did a calculation just for the zeros of the Riemann zeta function. So he calculated this side of the equality. So he's calculating sums of pairs of zeros. Remember, I told you there's a connection between the zeros and the prime numbers. That comes from looking at the logarithm of the Riemann zeta function and representing that as a sum of primes. So the zeros are related to the primes. So this side is a sum of pairs of zeros. So you can write it, it's a formula that was known to Riemann himself, as a sum of pairs of primes. From that sum of pairs of primes, if you calculate the diagonal terms, where the two primes are equal to each other, they can be evaluated using the prime number theorem, and that's what Montgomery did. So he proved a theorem for the diagonal terms in the double sum over primes that represents the pair correlation of the zeros of the zeta function. And he realized that the off-diagonal terms, where the two primes are not equal, would also be important in certain regions, and he was able to estimate those using a conjecture of Hardy and Littlewood for correlations between prime numbers, counting twin primes. And so piecing all this together led him to conjecture this formula for the Riemann zeros. The interpretation of this formula was due to Riemann Dyson, who recognized that this was just the pair correlation of eigenvalues of random matrices. So the history is Montgomery did a calculation and got an answer. He didn't know how to interpret the answer, and Dyson applied the interpretation that answer coincided with the corresponding pair correlation of eigenvalues of random matrices. And Montgomery was actually able to prove a theorem along these lines because it turns out that in certain range, for certain test functions f of x, the off-diagonal terms don't contribute. So if we choose f such that its Fourier transform only has support in -1, 1, then the off-diagonal terms don't contribute. We don't need the Hardy-Littlewood conjecture. You can get by with just the prime number theorem, and then you have a theorem for those functions that's consistent with the conjecture that Montgomery and Dyson made. But much more spectacular is the numerical evidence. So here's a picture of the pair correlation of the Riemann zeros. So this is taking my test function f to be a delta function. You would get the dots here are data coming from computing correlations between pairs of Riemann zeros up near the height of the 10 to the 20th zero. It's data calculated by Andrew Odlyzko, and comparing that to the formula 1 minus sine pi x over pi x all squared. And you see the agreement's spectacular. And the higher up you go, the better the agreement gets. So this picture is really indicating that Montgomery and Dyson's conjecture is very strongly supported by the numerical evidence. The history is that Montgomery did this calculation for the Riemann zeros during his PhD, or just after his PhD, and he went to the Institute for Advanced Study in Princeton to show his results to Selberg, and Selberg introduced Montgomery to Chowler, who insisted he go and speak to Freeman Dyson. It was Dyson who made the connection to random matrix theory. And he made this connection on April the 7th, 1972, which is exactly 50 years ago, earlier this month. So that's why I'm giving this talk. It's the birthday of this conjecture. And this was the letter that Dyson sent to Selberg, telling him to instruct Montgomery to start reading about random matrix theory. So it was Dyson who really spotted the connection to random matrices. Now you can ask whether this connection extends beyond pairs of zeros and pairs of eigenvalues, and it does. And this has been much studied. So it was studied by myself and Eugene Bogomolny, coming from a very physics perspective, and by Zev Rudnick and Peter Sarnak, coming from a very mathematical perspective. And together we were able to understand that this connection should hold not just for pairs of zeros and pairs of eigenvalues, but for all n tuples. So it's a very general statement about the correlations between the zeros and correlations between eigenvalues of random matrices. And the calculation, it turns out to be surprisingly tricky. So it turns out to be a combinatorial nightmare to do these calculations when you've got n tuples of primes contributing. And we were able to do this. We approached this with my colleague Eugene Bogomolny in the 1990s from a very much a physics perspective. And we realized that if you naively used the Hardy-Littlewood conjecture, you got the wrong answer. But being physicists, that didn't deter us. We simply calculated and found that there was a sort of expansion in terms of Feynman diagrams, which, if you believed it, would give you the right answer. And so we wrote this up in a couple of papers in the middle of the 1990s. And I have to say that for a long time, these papers were completely ignored, and quite right too, because they were completely incomprehensible to the mathematicians, and indeed to most of the physicists. And so we'd done this calculation and swore we'd never go back to it because it was so difficult for us, and it just sat there. But we'll come back to this a bit later. So it's a badly written, two badly written papers written by two people who didn't know enough mathematics to write the papers properly. But there was an idea in there which, at least to us, seemed interesting. We'll come back to this later. And we found that there is a way to get the right answer, but it was very hard to justify or even to explain to other people what our calculation was. But if you piece all this together, this means that it's not just the pairs of zeros or triples or n tuples. Any statistic involving the Riemann zero should coincide with the corresponding statistic for the eigenvalues of random matrices. And here's a rather famous plot of the distribution of gaps between adjacent zeros. So it's like a correlation of zeros, conditioned so they're right next to each other. This is the probability that adjacent zeros have a spacing s. S is on the horizontal axis, probability on the vertical axis. The data were computed for the Riemann Zeta-Function, the Riemann zeros, and the line is a highly non-trivial function that comes from random matrix theory. And again, the agreement is striking. So the conclusion of all of this is that we really believe that the zeros of the Riemann Zeta function have correlations that are identical in the limit as you go high up in the complex plane to those of the eigenvalues of random matrices. And here's a picture which I think, if you remember one thing that I've said so far, it might be this. Here are 50 points picked at random and placed on the unit circle. Here are 50 eigenvalues of a random unitary matrix. And you see that you compare these two pictures, they look somewhat different. Your eye's very good at detecting patterns. And you see the data over here has much larger gaps. These are the random numbers, and many pairs of random numbers lying quite close to each other. This picture has fewer large gaps, and the large gaps are smaller than the large gaps here, and very few instances where the eigenvalues lie close to each other. And these are 50 zeros of the Riemann zeta function wrapped around the unit circle, and you see that the patterns here look much more like this picture than they do this picture. So the zeros of the Riemann zeta function really are looking statistically much more like eigenvalues than random numbers. Why is this important? What's the number theoretical sort of advantage to knowing this? Well, let me go back to Gauss's letter to Encke, because Gauss was saying much more in this letter than I think has been appreciated. He records that he computed primes in several kiloids, and he says, and I emphasize here in red, I soon recognized that behind all of its fluctuations, this frequency is on average inversely proportional to the logarithm. Gauss was being very careful here. He was actually saying that the data is quite noisy and that you have to average over many kiloids of data in order to see what we would now recognize as the prime number theorem. And this wasn't just him speaking qualitatively. Gauss did inordinately detailed statistical analysis of the primes. Here, for example, is one set of data, one of many hundreds that are kept in the library at Göttingen, that Gauss recorded. So this is Gauss's handwriting again. So what Gauss recorded was the following. He took a range of 100,000 integers, that's 100 kiloids. He split them up into 10 ranges, each of size 10,000. So that's the first range of 10,000, the second, all the way up to the 10th. And then he split those 10 ranges, each of size 10,000, down into 100 ranges of a size 100. So he split the data up down into many ranges of length 100, and he recorded how many primes were in each range of length 100. So in the first 100,000, in the first 10,000, there was one range of 100 containing one prime, none containing 2 or 3, two ranges of length 100 containing 4 primes, etc. And what you see is that there are very few containing small number of primes, very few containing a large number of primes, and a big peak in the middle. And Gauss recorded this obsessively for all of the kiloids he looked at, and he split the data up in this highly complex way to analyze the statistics of what he was seeing. And what you're seeing here is, you might guess, a normal distribution. The data starts off small at one end, small at the other, and has a peak in the middle. And it's almost certain that Gauss recognized this, although I don't believe he ever conjectured that explicitly. But looking at this data, you might ask yourself, well, if you average over all of this data, which Gauss did at the bottom here, so he counted how many primes were in the total range and got 7,210, and he compared that to the logarithmic integral, which would have suggested 7,212, and he did this for every possible range to test obsessively the statistics. So what Gauss was interested in was the average, but clearly he was also interested in the small-scale distribution as well. And so it's an interesting question, what is the distribution of these numbers? So here's a more modern set of data, which I computed for myself. This is Kiliad starting at 10 to the 9. Easy to do this now with modern computers. So this is range of 1,000 integers in the first range, starting at 10 to the 9, and the 1,000 consecutive integers after 10 to the 9, there are 49 primes. The one after that, 50, then 35, then 58, etc. So I computed this for 25 Kiliads, starting at 10 to the 9, and this is the distribution of primes that you get in intervals of length 1,000. And if you average over all that data, you get 47, and the logarithmic integral gives you a number about 47. So this confirms the prime number theorem. But it's interesting to ask, what's the distribution of these numbers? For example, what's their variance? What are the higher moments of this distribution, not just computing the average? And so this has become a major problem over many years now in number theory. And a natural way to characterize this is in terms of the von Mangoldt function. So it's a better way to count the primes than just counting them with weight 1. We count for the von Mangoldt function for an integer n is 0 if n isn't a power of a prime. And if n is a power of a prime, you just take the logarithm of that prime. And this arises because it appears as the coefficients in the Dirichlet series for the logarithmic derivative of the zeta function. So this follows from the Euler product formula for the zeta function. And in terms of this von Mangoldt function, the prime number theorem is that if you sum the von Mangoldt function over the first capital X integers, the asymptotic of that grows asymptotically like x, as x tends to infinity. So this logarithm cancels the logarithmic decrease in the density of prime numbers, giving you, if you weight the integers with the von Mangoldt function, density, a sort of average weighting of 1. So this question about statistics of primes in intervals, if you bin the data into intervals, then becomes one, in modern terminology, of the variance or higher moments of the von Mangoldt function. So we get the von Mangoldt function. It has average value 1. That's the prime number theorem. Let's sum the von Mangoldt function over h consecutive integers near integer x. Well, the von Mangoldt function has average value 1. That's the prime number theorem. And so if you sum it over h integers, it should be roughly of size h on average. So we take the variance, we subtract off h, that's its average value, and then compute the average of the square of the difference, averaged with respect to x, the position where we place our window. And in modern terminology, the conjecture is a conjecture for the variance of that distribution. So think of this as the variance for counting primes in short intervals. In Gauss's problem, h would be 1,000 or 100. We'll be looking at number of primes in an interval of length 1,000 or 100. And this is the modern conjecture for what that variance should be. And this conjecture is equivalent to Montgomery-Dyson conjecture for pair correlation, for the pair correlation of the Riemann zeros. So if you believe this connection to random matrix theory, it gives you this conjecture for the variance of the number of primes in short intervals. And so that's why the connection with random matrix theory is important. It tells you about the distribution of prime numbers if you analyze the primes in the same way that Gauss did. And the modern conjecture is that indeed the moments of this converge to a normal distribution. And if you assume various things about the zeros of the zeta function, you can prove this, but proving it unconditionally is still a major open problem. So knowing about the connection between the zeros of the zeta function and eigenvalues of random matrices transfers, that information transfers to distributions of prime numbers if you bin the primes into short intervals in the way I've done here and in the way that Gauss did. So this story extends. I will just say in passing for experts in the audience, this is true not just for the Riemann zeta function, it's true for all other L functions. It's true not just for L functions defined over in number fields, but in function fields as well. And that's again a subject that where many local experts, and in this case you can really prove things unconditionally, though I won't say more about that. And it extends to many other statistics as well. But I won't talk about those generalizations. They're extremely interesting, and the picture is now a very general one that we have in terms of understanding which groups to average over for various different kinds of L functions. But that's not the story I want to tell you today. Rather, I'd like to switch and tell you about the moments of the Riemann zeta function. Because this is a subject which seems to be evolving currently in rather interesting ways. So the history of this is that going back about 100 years, people have been interested in the following problem, and it's closely related to the theory of the Riemann zeta function. You can ask, what's the size of the Riemann zeta function? What's the range of values that it takes as you go up the critical line where the Riemann hypothesis places the zeros? And so one way to characterize that is in terms of the moments of the distribution. And these were introduced by Hardy and Littlewood in 1918. So we get the zeta function on the critical line. We take its absolute value, raise that to some power, and then average along the critical line. So Hardy and Littlewood did this when beta equals 1 in 1918. Ingham did this when beta equals 2 in 1926. And since then, there have been a lot of studies of these moments, and I'm just listing a tiny fraction of the literature on them. They're an incredibly interesting set of objects, and they're surprisingly difficult to calculate. So in fact, rigorously, we only can calculate these moments when beta equals 1 and 2. Computing this for beta equals 3, so beta equals 1 was 1918, beta equals 2 is 1926. Beta equals 3 is still completely open problem. And calculating the sixth moment of the zeta function in this way will be a fantastic, sort of epoch-making step forward in our understanding of the zeta function. Non-rigorously, people have calculated it. So heuristically, there's a calculation of Conry and Gosch in 1998, who made a sort of non-rigorous stab at computing the sixth moment, and Conry and Gonek did the eighth moment when beta equals 4 in 2001. How do you do these calculations? Well, the zeta function, if you take the zeta function and raise it to the power k, just straightforwardly, by raising the Dirichlet series to the power k, you can represent this as a Dirichlet series where the coefficients here are the k divisor functions, the number of ways of writing n as a product of k integers. And so if you're interested in computing the moments of the zeta function, you can represent that as a sum over pairs of integers, n and m. This is the average along the critical line, and here's the pair of divisor functions that appear when you raise this to the power 2k. And so it's been understood for 100 years that the moments of the Riemann zeta function are related to correlations between values of the k divisor function for different integers n. And so if you use, there are several standard conjectures for the correlations of the divisor function, and turns out that when k equals 1 and 2, you don't need those conjectures. That's why we have unconditional theorems. When k equals 3 and 4, if you take those conjectures for the correlations of the divisor function, you get very sensible answers that, for various reasons I'll speak about in a moment, we believe. But for k greater than 5, it turns out you get complete nonsense. So we're in a very interesting situation. When k equals 1 and 2, we have rigorous theorems. When k equals 3 and 4, we can take off the shelf very well established conjectures for correlations of the divisor function, a very classical problem in number theory, and we get answers that for various reasons we believe. I'll tell you what those answers are in a minute. But for k greater than 5, you get absolute nonsense, and by absolute nonsense what I mean is you get answers that are negative. But clearly you're averaging a positive quantity. And so if you average a positive quantity, you can't get a negative number. And so for k greater than 5, that's been the conundrum. why does taking a very well-established conjecture for the correlations of the divisor function give you nonsense answers, give you good answers up to 4, and then incorrect answers for k greater than 4? I'll come back to that later. So what is the moment conjecture? What's the sort of synthesis of all those calculations that I've spoken about so far? Well, the moments of the Riemann zeta function, it's believed scale like log t to the power lambda squared. Lambda is the power here. There's an arithmetic factor, product over primes, that it won't surprise you that the primes appear, and that appears there, and Hardy and Littlewood knew what this factor was. But then the surprise is there's another factor, a more mysterious factor, that has to multiply this product over primes to give you the correct answer. And the question is, what is this factor? So Hardy and Littlewood found that this factor was just 1 when k equals 1. And I think they believed that the factor would be 1 always. But it was found by Ingham in 1926 that for lambda equals 2, the factor is not 1, it's a 12th. That's rather surprising that, that the answer is not 1. And if it's not 1, it's very surprising it's a rational number. There's no a priori reason why it would be. And then the guesses, the heuristic calculations of Conry and Gosch and Conry and Gonek were that the factor for 3 should be 42 over 9 factorial, and the factor for 4 should be 24,024 over 16 factorial. So where do these numbers come from? What are they telling us? It's very surprising these are all rational numbers. If you're quick at calculation, you'll see that if you take all of these, each of these 4 numbers and multiply them by k squared factorial, k the argument, you always get an integer. And the integers are 1, 2, 42, and 24,024. What are these integers? Well, this was the problem, this was the moment problem as it was left at the end of the 1990s. What's the connection with random matrices? Well, it's natural we've seen that the zeros of the zeta function look like eigenvalues of random matrices, so we might model the zeta function by a function that is associated with a matrix. And that would be the characteristic polynomial of the matrix. So this is the function whose zeros correspond to the eigenvalue, coincide with the eigenvalues of the matrix. And so the idea that goes back to the 1990s was to look at the moments of this function, compute this within random matrix theory, and then try to use that to understand the moment problem for the zeta function. So we're to get the characteristic polynomial of a matrix A, raise it to some power, take its absolute value, and average over the unitary group. We're to compare that to the moments of the Riemann zeta function. It turns out that this calculation in random matrix theory can be done, and this is one of the miracles of random matrix theory. It turns out to be an integral. You can represent the moments of the characteristic polynomials as an integral. I won't tell you where that comes from. It's a formula of Hermann Weyl that allows you to write it in this form. And then it turns out this integral can be computed exactly. This kind of integral is related to an integral computed by Selberg in the 1940s, now called the Selberg integral, and this turns out to be the answer. So within random matrix theory, we can compute all the moments of the characteristic polynomial of a random matrix, and it's just expressible as this product of ratios of gamma functions. And that simply comes from doing a calculation in random matrix theory, computing this integral. The asymptotics of that formula can be established. So you can compute the large matrix asymptotics of that formula. And for integer moments, you indeed get that for random matrices, the moments of the characteristic polynomial are always an integer over k squared factorial. That's a theorem in random matrix theory. And the question is, what are these integers gk? Well, it turns out that they have a nice interpretation. And it's a combinatorial interpretation. If you take a k by k array and fill into that k by k array the integers from 1 to k squared in such a way that you fill the numbers in so that they increase along each row and down every column, and ask how many ways are there to write the integers from 1 to k squared in a k by k array satisfying this criterion. So for people who are who know this language, these are computing the number of k by k Young tableau, that's precisely the number gk that appears there. So gk has a combinatorial interpretation. And the miracle is that this number gk matches the corresponding integers that appear in the case of the moments of the zeta function for all the cases that these are known. So 1, 2, 42, 24,024 are just the number of ways of counting Young tableau. And so if you believe that that continues, and of course we do, that leads you to some very general conjectures for the moments of the zeta function, and this is work I did a long time ago with my colleague Nina Snaith, where we were able to make rather general conjectures for the moments of the zeta function by taking these formulae that we had from random matrix theory and transporting them to the zeta function. And this is now what's called the moment conjecture. So we have very precise conjectures now that we can use to generate information about the value distribution of the zeta function, coming from random matrix theory, and agreeing with everything that we know on the number theory side, but making sense beyond k equals 5. And we can extend this now to compute lower order terms in the asymptotics, and we have, if you view log t as the natural parameter, you can actually now use random matrix theory to get not just the leading order asymptotics, but all terms down to exponentially small terms. And so we have now very precise formulae for the moments of the zeta function, conjecturally coming from random matrix theory. But let me go back to this conundrum. Remember that if you do a number theoretic calculation of the moments of the zeta function, you get sensible answers up to k equals 4, and then nonsense after k equals 4. We now have, from random matrix theory, a guess, a rather precise guess about what the answer should be. And we all know from teaching students that if you give them the answer, they can usually get the right answer. And so can we use this to understand the moment conundrum? And this has been a subject of considerable interest recently. And the answer turns out to be quite satisfying to me, that if you go back to this paper that I think nobody, including myself and Bogomolny, understood in 1996 with this expansion in Feynman diagrams, with my colleague Brian Conry, we actually went back and decided to put this on a proper mathematical footing. And it turns out that if you put that expansion in terms of Feynman diagrams on a proper mathematical footing and then apply it to the moment problem, you do get the right answers, or rather you get answers for any k that agree with the random matrix conjecture. So the point is that doing the sort of using the divisor correlations naively gives you the wrong answer, and you do actually need this rather perverse expansion that we concocted in the 1990s. And if you put that on a firm footing, it turns out that that procedure does give you correct answers for all of the moments. And so we now do understand from a number theoretic perspective how to get all the moments of the zeta function. In the last, should I stop or come in a minute? In a couple of minutes. Now, I'll tell you one final theme in the last couple of slides, which has been really, I think, rather spectacularly interesting. And this goes through to the question of, which again has been around for 100 years or so, what are the extreme values of the zeta function? So here's a picture I showed you earlier. The zeta function oscillates rather irregularly, and occasionally it takes very large values. What's the distribution of those very large values? What's the probability that the zeta function will take some unusually large value along the critical line? So this, if we take the question is, if we take the maximum of the zeta function over some large range, how does that grow? What's the largest value in some large range? Well, this is the subject of a very famous hypothesis due to Lindelof, who conjectured that the zeta function, the large values of the zeta function should grow more slowly than any power of t if you look over a range of length t. So there should be little o of t to the epsilon for any epsilon greater than 0. And this is still an unproved hypothesis, very important in the theory of the zeta function. But Lindelof wasn't able to give anything more quantitative than this. Just a little o estimate still is an obstacle for us, but we don't know more precisely what the extreme value should be, what their size should be. Well, we realized about 10 years ago that if you restrict yourself to shorter intervals of the critical line, so not an interval going from 0 to t, where t tends to infinity, but instead an interval going from t to t plus 2 pi as t goes to infinity, we could make very precise conjectures for the maximum size of the zeta function as t tends to infinity by comparing to random matrix calculations. So it turns out that this kind of question, looking at the maximum size of the zeta function over an interval length 2 pi, that interval still has increasingly more zeros as you go up. So as t goes to infinity, there are infinitely many zeros in the limit in a range of this length. It turns out this is the right question if you want to compare to random matrix theory. And we were able to make, 10 years ago, a very precise conjecture about what the maximum should be over such an interval. And we conjectured this formula by comparing with a calculation that we were able to do in random matrix theory. So this is now a very precise form of Lindelof, but over short intervals of the critical line rather than long intervals. And the conjecture was that if you take the maximum of the zeta function over an interval of length 2 pi and take it the logarithm of that, that should grow like log t on 2 pi minus 3/4 log t plus a random variable, which we were also able to conjecture the value distribution of this random variable. That's it's an order 1 random variable. And again, if you're able to write down a formula, it's surprising how psychologically that unblocks people's thinking. And so having this formula, now the number theorists have managed to make spectacular progress on this problem. And so it turns out that now both of these terms have been proved rigorously and unconditionally. And this has arisen because of a radical reinterpretation of the formula for the log of the zeta function, which is a sum over prime numbers. People have understood that there are various ways to combine the terms in the sum over prime numbers that represents the log of the zeta function. And understanding that has now enabled people to come up with with proofs of this rather precise conjecture for the extreme values of the zeta function. So I think what I wanted to tell you was that there is a deep and a rather surprising connection between the Riemann zeros and operator theory. In particular, the connection with random matrices, which in some sense represent random operators. This conjecture has its 50th anniversary this month. And that if you're prepared to make these rather speculative connections between random matrix theory and number theory, you can come up with very precise conjectures for problems that were out of reach within analytic number theory, but which now have come within reach once we've understood the structure of the answers. And this has been highly stimulating both in analytic number theory, but also in random matrix theory, because often it's led us to new calculations in random matrix theory that have to be done, and this has been highly stimulating in that area too. So I'll stop there and say thank you very much for your interest.
Thank you very much for the wonderful talk. Are there any questions or comments? I keep an eye on the chat also in case you are online and want to ask a question.
So are there some good examples where the matching with random matrix theory breaks down? Where it, I know obviously, or maybe less obviously. I'm just curious if you know some.
So I know of no, if you phrase the questions correctly, and of course sometimes it takes a long time to phrase the question correctly, I know of no case where they disagree. But there are examples early on in this subject where the questions were phrased in a way that we wouldn't do now, and where you do get a disagreement. And those, we've now understood much better the scales where one expects to see agreement and the scales where one expects to see disagreement. So if I go back to the moment formula, that was a combination of two parts. There was a part coming from random matrix theory and a part coming from the primes. So you could say that means that there's agreement with neither. But it's understanding how those combine together properly means that we now do understand how to always, well, so far, get the right answer. But that doesn't rule out the fact there'll be something that disagrees at some point. This is now a sort of hugely tested set of ideas And so far, if you phrase the questions correctly, we've not found disagreement.
I have a simple question. Can you tell us a little more? How did Gauss count all these primes and so on? Were there lists, or did he do it all by himself? It's amazing. 3 millions, you said.
It is absolutely amazing. He writes quite extensively about his early life, and he says that he would set aside, when he had a few spare moments, he'd calculate a few more primes. So this was a sort of long-term research project, we would now call it a 5-year research grant type project. And he would just sit, and there's an efficient algorithm for sieving out integers that are divisible by other integers. So it's easy to rule out integers that are even, for example, and then multiples of 3. And it was basically pursuing that kind of approach that Gauss was able to then sieve out all of the things that were divisible, leaving him just with the primes. That's a highly non-trivial calculation to do, and to do that for sort of 3 million integers would, I think, tax people.
But he did it by hand.
He did it by hand. There were he wasn't the only person doing this. There were other people doing it. He was able to compare with data that other people had calculated, but he went much further than anybody else.
Are there other questions? Oh, yeah.
Well, first of all, thanks for the talk. My question is about the Montgomery-Dyson conjecture. So, as you explained to us, Montgomery kind of came up with this formula, and then Dyson recognized it. So I was wondering if there's a conceptual reason why the unitary group comes up there.
It's a great question, and the answer is we don't understand that. So the answer is no, and this is why these calculations are quite difficult. The calculations on the number theory side don't resemble the calculations on the random matrix theory side. The random matrix calculations, we now have very efficient ways of doing those calculations, and we can represent, there's a very efficient way to represent all correlation functions as determinants involving a simple kernel, a sine pi x over pi x, sine kernel, so to speak. And that is a very efficient formula. On the number theory side, the formulae are horrendously combinatorial, and it's only at the last step that you see that the answers agree. So there's no conceptual understanding of why random matrix theory appears, why the zeros of the Riemann Zeta-Function have correlations that can conjecturally be written in a determinantal form. Even that we don't understand. It's simply a brute force calculation and then comparing formulae. The question as to why it's the unitary group is a really interesting one. It turns out that the Riemann Zeta-Function is one of an infinite class of function called the L functions, all of which look pretty similar. They all have a function equation, an Euler product, a Dirichlet series, and they all have a Riemann hypothesis. And if you fix your L function, it's conjecture of Rudnick and Sarnak, that for any L function that behaves nicely, that's not sort of obviously a counterexample, any principal L function, for those who know that terminology, that you'll always get the unitary group in every single case. And so the unitary group is a universal answer for any fixed L function. However, if you, rather than fixing your L function and averaging up the critical line, if instead you fix a height on the critical line and average through a family of L functions, so vary your L functions, then you can get either the unitary group, the orthogonal group, or the symplectic group. And so there's a sort of classification of L functions in terms of symmetry groups that we're far from understanding. And again, often to know which symmetry group arises, you actually have to do a brute force calculation and just compare the answers, and that tells you what the answer should be. But understanding that, I think, would be a really profound step in analytic number theory.
Yes, you said you showed Gauss's handwriting,
Yes.
and to the right you had Irreformen und Abweichungen.
Yes.
Could you tell us a little about that? You hinted at it.
Yes.
You didn't want to tell us.
So Gauss, of course, was fiercely competitive. And there were various formulae that were knocking around for the density of prime numbers. And Gauss wanted to do two things. He wanted to say he had a conjecture 40 years ago that was the right one, and he was comparing to a conjecture formula of his ex-student Encke, and he wanted to say that not only was I 40 years ago, but my formula is better than your formula. So the last set of data was a comparison with Encke's formula, and Gauss was quite obsessive about this. There were various conjectures around, and he would compare obsessively the data that he had accumulated with various other formulae that were there to establish that not only his priority, but his superiority. Not good supervisor's practice, but not uncommon either.
Okay, one last question.
So I was wondering, do the conjectures, the conjectural links between random matrix theory and Riemann Zeta-Function, do they also say something about potential zeros that are not on the critical line? About the Riemann Zeta hypothesis?
So there are ways to approach that question using random matrices. These kind of connections at the level I've expressed them really make most sense if the Riemann hypothesis is true. But you don't need it to be true, and you can investigate distributions of zeros assuming it's not true. And the most sophisticated way to try and estimate the number of zeros on the critical line is actually to look at the distribution of zeros of the derivative of the zeta function. And they don't have to lie on the critical line. In fact, they don't lie on the critical line. They lie to the left of the critical line. And there's a sort of, it goes back to Levinson, and a sort of, this way of getting 42% really is looking at the distribution of zeros of the derivative of the zeta function. They don't lie on a line. They have a distribution in the complex plane, and you have to analyze those. So in the same way, you can also analyze the distribution of the zeros of a characteristic polynomial. They don't lie on the unit circle. They lie in the convex hull of the set of zeros, of the zeros on the unit circle. They lie in the complex plane inside the unit circle, and there's been a lot of interest in trying to understand the distribution of the zeros of the derivative of the characteristic polynomial and compare to the zeros of the derivative of the zeta function. But that's not actually, I would say, it's still a largely open terrain. There have been some first steps in that direction, but the calculations are much harder, and there's been no satisfactory progress. I would say that the progress has been more limited there. I think.
Just one question.
Just very quickly.
You didn't mention the Russian Pafnutil Lvovich Chebyshev. Did he contribute nothing?
He did indeed contribute towards estimates related to the prime number theorem. He had upper and lower bounds, but not using complex analysis of this form. So, excuse me for this. Yes.
Okay, thank you very much. And let's first thank John again. I suggest that any further questions can be moved to the reception, which will now take place if you go outside, go down the stairs and go to the left. This time I do it correctly, to the left. And everybody is of course very much welcome to join. Thank you for coming. Thank you.